technically your class doesn't start till 9:30, right?
Right, but a lot
Yeah,
of them logged in early.
early.
Let's see.
Now, was this yesterday what was happening? Like you couldn't see, you could only see, you couldn't
No,
see.
no, no, this isn't what happened
Okay.
yesterday. Uh, start, start, start video. I think that's what I want. Yeah,
There you are.
there we go. Now I need to adjust this to where they can see the board. That's
Right.
pretty decent right there, don't
Yep,
you think?
that's good.
All right.
So you're on. You can see. They should be able to see.
So let's put the. Could could you open those windows and so I'm not so blue? I'm blue. Yeah, that's. I think that's better. Well, it kind of makes a glare, but okay. Now this is strength of materials. I wonder if this needs to be further back or what. Let's see. Yeah, we kind of gotta. Uh, can you close those?
Yeah.
There's too much glare coming in here. Hey, I think I got a customer already. I got a customer. So I'm gonna write. Now what I want is the board. So what I want to do is go up here and pin me. Isn't that right? What I want to do? Click on me. Yeah, there it is. Okay, now today is this is strength of materials. And I think we've got customers already. And it's April 9th. Thank you for that. April 9th, 2020. There. Now, I got Dalton on there. What did I do? Yeah, hi, Dalton.
How are you?
I'm not too bad.
Good.
We're early, of course, but let me figure out what we're going to study today.
Yeah, I gotta grab some stuff, so you take your time.
Yeah, let's see. Oh yeah, Flexure Formula, Chapter 6. Somehow I think I kind of skipped over Chapter 6. We don't want to skip Chapter 6.
Probably not a good idea.
No, we don't. So the topic is Flexure Formula. In fact, I'd kind of like to show the students where it comes from. Yeah, that's what I'd like to do, show them where it comes from. I tell you what it is, it's this here. That is the Flexure Formula. We're going to show you where it comes from and maybe work a problem or two. That'd be good. Okay. Yeah, I just didn't know how to pin myself yesterday, Susanna. You just go up to where my little picture is and click on it. And
it's big.
I didn't know to do that. And so now we have a whiteboard. And if they want to see my beautiful face, I can poke my head in here. Okay. We only have one customer so far. One of my more excellent students named Dalton.
That's me.
Yay! I've got one of my daughters here. I've got two of my daughters and a grandson helping me with this stuff.
Nice.
Oh yeah. How old are you, Dalton?
I'm 23.
23. Well, that's about how old my son-in-law is.
Yeah, I'm a little bit older than some of the kids in our class just because made some mistakes early, but going back and doing a lot better now.
So you've been out in the real world.
Yeah. I have.
Okay. Well, I know what I want to talk about. I want to talk about actually about 5 things besides the Flexure formula, dealing with the Flexure formula. And you got the word. Don't turn in any homework yet, but we're working on it. And also, one of my daughters has fixed up a YouTube channel for me,
Okay.
and you can watch the videos on YouTube if I can figure out how to give you the little secret code to log in. You can help me, can't you, Susanna, on that? Yeah. One of my other daughters can help us so you guys can have access to those videos. That'd be great. Hey, Dalton, this is free time now, no extra charge. Did you have any questions?
I did not.
What did I ask you? What did I ask you to do last time? I wanted you to work on something. Was it 7:35? Was that what it was?
The last homework I have is 7:13
Yeah.
and 7:35. Yeah.
Good going. Did you work on those?
I haven't done 7:35 yet, but I did do 7:13.
Well, now
And
I put one of those on Blackboard for you.
it was for on Tuesday. I think you put it on there, right?
Yeah. Did
Yeah.
I put both of them on there? Do you know?
7:13 was, I think, the week before.
Oh, okay. But I think I put 7:35 on there.
Yeah, you put it on there
Tuesday, I guess.
Tuesday.
So
Or I
see,
think you
what you want to do is don't peek. See if you can figure it out yourself,
right,
and then peek at my answer.
right. Yeah, I can do that.
That's the plan.
Yeah, my plan is to do it today with the homework that you give today, and then I'll
Yeah,
just turn it
that's
all.
fine. I'm going to give some homework today and maybe help you a little bit. But again, I'll need to put that on Blackboard for you because I don't want you to turn anything yet. Hey, I caught up. I got everybody's grades
That's good.
recorded. Let me see about your grades here, Dalton.
Yeah, see if I have any missing assignments.
What's your last name?
Reese, Reese.
Yeah. Well, I don't have 713.
Yeah, I haven't turned that one in yet.
Now, did I ask you to turn? Yeah, that one I asked you to turn in.
On
730,
Tuesday.
yeah, 735, don't turn it in.
Okay, well, I'll scan that one and email it to you today, if that's okay.
Yeah, oh, that's super good. Let me look in the past here. I'm gonna go back a little bit. Nope, you're not missing a thing except that the 7, what did I just say, 713?
13.
Yeah. So turn that in. We'll give you some points there. And
I can do that.
my daughters are figuring out a way to submit homework on Blackboard too.
Okay.
I don't know how to do it yet, but we're getting there. Well, let me see if I can see a picture of you here, Dalton.
I actually don't have a webcam.
Oh, you don't have a
I'm on a
webcam.
desktop. Yeah, I'm
So
sorry.
that's fine. See, if you had a webcam, I could click on you
And you can see me.
Yeah,
Uh,
that'd be pretty cool.
no. I'm sorry.
Oh, that's okay. All right. Now, are you in any of my other classes?
I'm in your dynamics class.
Okay. Now, we don't meet till Monday at 9:30.
Mm-hmm.
Yeah.
Yep.
Good, good, good. Okay, well, I'm gonna go get my canteen of water. I see I've forgotten it. I'll be back.
Alrighty.
I'll be back. Because I'll get dried up if I don't get my water. Hi, cutie. Do you need any more light?
I'm good.
You sure?
I mean, sure, that's good.
That's good. You can hang out in here. You won't bother me any. I wonder if I got any. Hey, I've got some more customers in here. We've got Coy and Daniel and Caitlin. Can you guys talk to each other? Hello, students. Can you guys talk to each other? Let me go to Coy here. Coy, do I need to unmute everybody? Yeah. Coy, everybody unmute. And can you guys talk to each other? Earth calling students, Earth calling students. Well, let me pin myself. There I am. I need to know if you guys can hear me. Down here it says chat. Maybe I'll click on chat and see what happens. Chat. Well, I clicked on it, but I don't know what happened. Message participants. Let me click on that and we'll see what happens. Oh, look at who we got here. We have Carolyn, Dalton, yeah, Daniel, Eric, and Gavin. And class starts in 3 minutes. Where does it say mute? Oh, there it is. Okay, now unmute. Unmute and say hello. I don't want to mute all. I want to there we go. I unmuted all. No. Okay, I unmuted all. I thought I did. I just need somebody to say hi.
Hello,
Yeah, now who's that?
Eric.
Hi, Eric.
Hi.
Okay. Well, it's about 9:30. I think we ought to get going. I don't see in my list over here, though, Eric. I see Allison and Caitlin and Dalton and Cameron. And they got some of you guys up here on top. Daniel, Caitlin, Coy, Dalton. All right, well, I guess we'll get started then. It's 9:30. The topic is the flexure formula, and there it is. But where did it come from? Well, I looked all over the house for a meter stick and couldn't find it, but I did find this. It's just a board, just a stick. And when you have a beam and you load it, you put the forces on it, it makes it bend. Can you see that it's bending like that? And when you do that, you have compression on the top of the board and tension on the bottom of the board. Here, let me do that again. I'm gonna bend it. Can you see you have tension on the bottom of the board and compression on the top of the board? Kind of makes sense, doesn't it? Now, right in the middle of the board, at what they call the neutral axis, it's neither compression nor tension. So here, I'll draw you a little picture. This particular stick was kind of shaped like that. Of course, it's going back this way. And I'm bending it. It's a beam. And on the top, you have compression. And on the bottom, you have tension. Let me do that one more time in case somebody out there didn't quite get it. If you have pretend this is a beam and pretend you put a heavy load on it and it'll sag, beams sag, and the beam will be bent like that. And you can see it's got a curvature. Maybe it's easier to see this way. Can you see that it has a curvature? In fact, if the beam is sagging and bent kind of like that, somebody say something. Dalton, say something.
Hello.
Yeah, okay. So you guys can hear me. All right, good.
Yes, sir.
This beam that's being bent has got a radius of curvature. That it goes out this way. The symbol is rho. It's a radius of curvature. The radius of curvature. And I think you understand that. And they start by deriving the flexure formula by talking about the radius of curvature. And and you know, on the top you have compression, and on the bottom you have tension. You can see it's being stretched on the bottom and being compressed on the top, but right in the middle, suppose this beam was, I don't know, square or 2x4 or something. Let's look at this end piece here on the beam. Maybe it looks like that. You got compression on the top, tension on the bottom. But see right here, there's no, it's not compression or tension. The stress here is zero. Zero stress in the middle. We have a name for that. It's called the centroid. So the stress is zero at the centroid, and it's the stress is compressive at the top. You got compressive stress at the top, and tensile stress at the bottom. Whoops, these are normal stresses. That's wrong. Let me get this right. These are normal stresses we're talking about. The flexure formula is not shear stress like we were doing in chapter 7, which we'll get back to. It's normal stresses. So you have compressive normal stress at the top, tensile normal stress at the bottom. And that's the formula for it. See, now the reason for the minus, let me tell you about the minus. This right here is called y. It's the distance from the centroid. And see, if y is positive, and you put a positive y, m is positive, and moment of inertia is positive, all that's positive. So you get a negative answer, and a negative stress is compressive. So if the y is positive like that, then you get compression. Now, if the y is negative, see, going down this way, the y will be negative. So if you got a negative there, and there's a negative sign in front of the equation, that makes the stress positive. So you got positive stress on the bottom. All right, we all understand that, I hope. Okay. Now, there's also strain going on. Let me write the equation for strain. By the way, this is all in your book. You could read this in your book. I know it's in chapter 6. Let me tell you what page it's on, and you could read it in your book. It's in chapter 6. Kind
It's
of.
on page 295.
Oh, good going. Appreciate your help. Yeah, good, excellent. The equation is on a couple pages before that. On page 292, they give you the equation for normal strain. That's on page 292. And again, you know what strain is. That's like you're stretching or compressing. There's supposed to be an equal sign here. There we go. This is normal strain. And see, if y is positive, then you'll get a negative normal strain, which means it's compressive. And if y is negative, you got a negative, negative, you get a positive normal strain, which is tension. This little c here is the maximum value of y. Let me draw you a rectangular beam there. See, this distance here is called y, and it can be positive or negative, but c is the maximum value for y. That's what c is. It might be down here. If you have a non-symmetrical beam like this, for instance, I think I might have done that with you. The centroid is kind of in here, and the value of c is the maximum y, and it would be going down this way. That's c. You don't call this one c because it's not as big. See, what c is the maximum value of y. You don't want it there, you want it here. C is it's the distance from the centroid. That's the centroidal axis. And it's to the farthest point on the piece that you can go. If you had a beam like this and you had it supporting a load and it would sag, you would discover that the maximum strain would occur down here at the bottom. And it would be tensile strain. Remember, at the bottom you got tension. So the maximum normal strain is there at the bottom of that piece. Okay, and look at the formula here. See, if you put C in there for y, remember y is just the distance from the centroid. Whatever distance you want, that's y. And if it's equal to C, then you get minus, now I'm getting confused now. Well, you'll just get the absolute value of the strain. That minus takes care of it. So there's that formula there. Let's just say we want to look at the maximum or the absolute value. The absolute value of your strain is given by that equation there. Okay, great. Now, if you have any questions at any time, there's a way of asking questions. I think when my daughter's told me I can go to chat. And hey, I got some more customers here. Hey, a whole bunch of wonderful students just signed in. If you have a question, there's a way of you telling me that. You can even text it. But my daughter left. She's gone someplace. She can't help me. There's a way that you could ask a question. I guess you could unmute yourself and talk. That'd be all right too. But here's the thing. We have a lovely equation that goes like this. It's got a name. And if you guys could answer me, you could tell me the name of that equation. But nobody's saying anything. Everybody's shy. It's called Gavin, what is it?
Stress strain equation.
Yeah, it's named after a famous guy. Mr. starts with H. Starts with H-O.
Hooke's law.
Yeah, that's it. It's Hooke's law. Yeah, this is Hooke's law. One of the most important equations in our course, if not the most important. So you could write this equation here. I think you can see that there's a one-to-one relationship between stress and strain. See, that's stress, that's strain. Now be careful, that's only true in the elastic region, but that we're in the elastic region for a while. And so you could go from here, we're just looking at the absolute value there, to here, because it's sort of a one-on-one correspondence there, and you have this lovely equation here. And with that equation, I'm halfway done to the flexure formula. Okay, so here we go. We're going to derive the flexure formula now. All right. And all this is on page 292, I think. Yeah, well, it's more on where we are right now is more like on 294. This is on page 294. We're talking about the flexure formula for a little bit today. Now the bending moment acting on a cross section is equal to force times distance. So now the force would be the stress times the area. Now, if you're just talking about a small amount of bending moment, it'd be like that. If you wanted the total bending moment, you'd have to integrate like that. And we just cooked up the value for normal stress, and it went like this. Now, the area, we can just leave alone. And this, you'd have to integrate this over your cross section. It might be a rectangle, it might be a circle, who knows? Okay, now here's what we're going to do. We're going to take out the constants. Now, the maximum normal stress is a constant, and C is a constant, and you get. Now, just a minute. Now, I'm getting fouled up. Let me double check everything here. Okay, I've goofed up a little bit here. Okay. No, I think that's correct. Okay, now just a minute. All that is the force. And so here's where I went astray. You've got to multiply a distance times your force. which would be, there we go. See, force is stress times area. And a moment is a distance times stress times area. That part there is a force. Okay, here we go. Now this is equal to y times, it's equal to y over c. We just had that equation. We just had that equation for stress a minute ago. And I tried to explain it. And so we're taking a distance times a force. Yeah, times an area. Okay. And that's equal to, now we're going to pull out the constants. Those are constants. And so what you have left is this here. They do this on your book, roughly page 294. They gave this a special name. They called it the moment of inertia. That, you wondered, well, where did they get that? Where did that equation come from? Well, this is, I'm showing you. And so what you have now is your bending moment is equal to that equation there. And we're going to do a little algebra now. We're almost done. 2 more steps and we'll have our flexure formula. See if you can get to here with me. Were you able to get to there? Yeah. Now remember, we had this equation here. What that is your stress. Your stress is equal to y over c times sigma max. We talked about that a minute ago. So what I'm going to do is I'm going to take this sigma max and plug it in here, and let's see what I get. I get y over c times mc over I. Well, look, the c's go bye-bye. And what you have left is my over I. Now, I forgot the minus sign, doggone it. Remember that minus sign? Don't get stressed out about that minus sign. It has to do with if y is positive, you get compression, which is minus. And if y is negative, you got 2 negatives makes a positive. You get tension. And we're done. Ta-da! We just showed you where the flexure formula came from. Okay, great. Let's do an example. Before we do, though, did anybody want to make a comment or question? I want to unmute everybody if I can.
Looks good.
Good. You guys understood that okay?
Yep.
It's kind of boring, but it's an important formula for it's bending stress. Some people put a little b right there for bending stress. Okay, now let's do an example. Here we go. If you like all that. Our topic today, for those of you that just tuned in, is the flexure formula. It's what you get for stress when you have a beam that's being loaded and it's sagging, it's bending. and you get bending stress. And this I here, we just showed you where it came from. Let's repeat that. I is this y squared dA is what it is. They have a name for that, by the way. It's called the second moment of area. It's the second moment of area. Now, somehow I skipped all this stuff and we jumped into chapter 7, and you guys learned this here. I think they called it, is it Q? Was it Q that they use in chapter 7? I believe so. And the name of
It's
that.
first moment of area.
Exactly. Thank you. Did they use a capital Q or a little q? Does anyone remember?
Capital Q, lower Q was for flow rate. Or
Yes.
shear flow.
Thank you so very much. You're absolutely right. The little q was for shear flow. Now, this is called first moment of area. That's called the second moment of area. Just to be goofy, you guys are pretty sharp. What would we call that?
Is it the third moment of area?
Yes, it's the third moment of area. Good going. Yay. Did somebody just flush a toilet? That's what it sounded like. That was weird. Okay. Okay, now let's do an example, shall we? Okay, we're going to do an example now. I've got a kind of like a 2x4, only it's not exactly a 2x4. It's a 0.02. It's a 0.02 meters by 0.04 meters. So it's sort of a 2x4, isn't it? And let's what am I going to do with it? Well, let's put a bending moment on it. We'll put a bending moment on it of I don't know. I'll make something up. Say we'll put a bending moment on it. Now it's funny the way they draw these in the book. See, this is a beam. It's a very simple beam. It's kind of like a 2x4 beam. They draw their bending moment like that. And we'll just say it's 1,000 Newton meters. Now, I don't like that. I like to draw my bending moment like this here with a double arrow on it. You guys have seen me do that before. A double arrowhead. So I guess you could use both conventions. But see, if this thing was, if this was a beam and it was sagging, can you see that you'd have compression on the top? I don't know if everybody saw this. Before everybody tuned in, I took this board here and see it's sagging and you have compression on the top. You can see that there's compression and there'll be tension on the bottom. See, on the bottom of this beam, there's tension on the bottom. Okay. Well, let's figure out what the stress is. Now remember why, we got to decide which convention we like. The book does this, I do that. Doesn't matter, they both amount to the same. We just leave it alone, I guess. Now, we just figured out what M is. I told you the M is 1,000 Newton meters. Oh, we got to get I. And we know the general equation is y squared dm. No, y squared dA. Now, if you integrate this over a rectangle, you get 1/12 the base times the height cubed. It'd be fun to derive that, but I'm just going to look it up it's in the front of your book. For a rectangle, I'm looking at it. It's in the flap of your front of your book. It's 1/12 BH cubed. Okay. Well, let me write that down. We'll figure out what it is. It would be 1/12.02 times 0.04 cubed. And we'll get the moment of inertia. Here goes. And you guys work along with me here. Make sure I don't goof this up. 1/12 times 0.02 times 0.04 cubed. Did you get 1.0, a whole bunch of sixes, meters to the fourth?
Hey, Professor.
Yeah,
Since the force is acting to the side, does that
That's not-
change?
that's not a force. That's a moment.
Or since the moment is acting on the side,
Uh-huh.
doesn't the main axis that we need to cube, isn't that the 0.02 instead of the 0.04?
No, I think what you're talking about is you're trying to bend this beam like that. See, I'm bending it like this. See, whoa, it just snapped. I think what you're talking about is I'm trying to bend it like this, and it's hard to bend like that. No, there is another equation that goes 1/12 HB cubed, but that would be if your beam was laying flat like that. Sorry to confuse you, but I think we're okay. We've got our moment of inertia. Let's circle that. Now we can find our stress at any place. The bending stress. Did that satisfy you, Gavin? Probably not.
Nah, not really.
You're aware there's two equations.
Right, you have one for along the y-axis and one along the
Right.
x-axis.
Yeah, this is the x-axis equation that we're doing. See, the x-axis goes through here.
Right, but I guess I don't see the bending going through the x-axis. It looks like to me it should be going through the y-axis.
Okay. Now what that would be is if I took this beam and I bent it this way. You can't see me bending it. Whoops. Can you see me bending it now?
Yes, Professor.
See, that's about the y-axis. We're bending it about the x-axis.
Sir,
Yes.
I just did both the numbers. The equation that we are currently doing is about 1/5 roughly of the value that you get.
The other way?
Correct.
Right.
Or it's 5 times more. As
Okay.
in this is the harder, quote unquote, harder one, right?
Right here. I want you to understand, if you take and your beam is like this, that's different than if you take your beam like this.
Correct. So the number that you get, the 1.066,
That's
it's
this
actually
one. That's
it's
this
actually
one.
to the negative seventh.
Wait a minute. I think
It's
you're right. Yeah,
it's e to the negative seventh, and then if you do
yeah.
it the other way, you get an e to the negative eighth. So
Let me do it.
it's
Let's see.
smaller.
0.02 times 0.04 cubed. Yeah, I didn't get that this time. Let me do it again. I'm glad you spoke up. Yeah, I got that number. I forgot a little teeny tiny detail here, guys. You have a 10 to the minus 7 meters to the fourth if you do it that way. Now, that's this one here. This one is 1.066 times 10 to the minus 7. This one here will be 1/12 HB cubed. Well, here, I'll just write the answer. You take 1/12 times the height, which is 0.04, times the width, 0.02 cubed, and you get 0.2 bunch of sixes times 10 to the minus 7 meters to the fourth. And like Gavin was trying to tell us, this is 5 times that. See, if I multiply that by 5, no, it's not 5 times, is it?
It's actually about 4 times, not 5.
Let me do it again. Maybe I made a mistake here. I don't want to leave you astray. I think I did that right. Okay, and now I'm going to see how many times bigger it is. If you take that and you divide by that, it's 4 times roughly. Yeah. What they're saying is it's 4 times harder. This has gotten 4 times. It's 4 times as hard to bend that beam that way than it is that way. Did that make sense?
I
Hopefully.
believe Gavin is right, sir. I believe you have them backwards. The larger number means it's harder to bend, correct?
The larger number means it's harder to bend, correct?
So don't you have those backwards?
Well, isn't this bigger than that? Isn't 1 bigger than 0.2?
Yes, sir. So if 1 is bigger than 0.2, that means it should be harder to bend.
Yeah, this one's harder to
vertically.
bend. And you think this one's going to be easier to bend?
Are you trying to bend it along the x-axis or the y-axis?
You have a beam. Here, let me draw a beam for you. Here's a beam. We're going to simply put some simple supports here on this beam like this. And then we're going to put a heavy weight here, a big force here. And you know what's going to happen? The beam is going to sag, isn't it? It's going to sag. Now, which way do you want to put that beam on there? Do you want to put it like this or like that?
Well, the way you have it drawn is the way that takes more force to bend it.
Yes, this one here takes more force to bend it.
So we're just saying that for the purpose of this example, we're putting it on its side and we're bending it. We're not putting it on the flat.
Yeah, we're putting it on its small side and bending it, exactly.
Okay. I just wanted to make sure that that was the intention, because the doing all the eye and stuff is, you know, confusing when it's not when it's not properly what do you call it?
Oriented?
When there's not enough information given about the situation.
Well, we're orienting it like this, just like I drew it here. And we have found the moment of inertia. And we have our equation now. And we're going to find the normal stress up here, and it'll be compressive. It'll be pushing like that. And I'll tell you what it's equal to. it's equal to whatever you get when you plug this in. Now this value of y here would be 0.02. So we're going to find the normal stress up here at the top, and it'll be, well, the equation says minus 1,000 Newton meters times 0.02 meters divided by 1 point blah, blah, blah. And we're going to get the normal stress. Here goes.
Uh, 188 megapascals.
I'm getting 187. Yeah, you can round it off. 188 megapascals. Good going. It's exactly what I got, huh? We'll wait.
Now, shouldn't it be negative?
Now just a minute. Oh, an intelligent question. They wanted to know if it's negative or not.
I believe so.
Well, it is negative because it's compression. Very good. I don't know who said that. Was that Coy? Who was that?
It was Eric.
Eric, you just got a thank you point. It is negative, and negative is compression. Positive is tension. Now down here, you're going to have a normal stress. It's the same numbers, but it'll be positive 188 megapascals. Now in between, right here at the centroid, you don't have any stress at all, because between compression and tension, remember this is tension. And it's positive, and this is compression, and it's negative. Get a drink of water just a minute here. But right here in the middle, the stress is zero. And you get this distribution that looks like this. It's linear. And it kind of goes like this. You'll see these stress distributions in your book. They go like this. Your maximum stresses on this one are at the very top and the very bottom. Tension, compression at the top, tension at the bottom. Flex formula, and you understand it. Now, if you had A36 steel, suppose this beam was made of A36 steel. Well, it has a yield strength of 250 megapascals. We're not there yet. 188 is smaller than 250. So we are still elastic. We haven't gone plastic yet. But you know what? There is a thing called the maximum elastic moment. We're going to figure that. We're going to figure that. Now we know the moment of inertia, that's a keeper. We're going to figure the maximum elastic moment. There's a symbol for it. It goes like this. It stands for the maximum elastic moment. we want to find what it is. Now the moment that we had on our piece was 188 megapascals. No, that was the stress. The moment was, I erased it, but it was 1,000. I believe the moment that we had was 1,000 Newton meters. And we know all these distances here. This is 0.02 meters, etc. 0.04 meters. What I want to find out is what is the maximum elastic moment? Well, here's how you can get it. If you go to your yield stress and you set that into that equation there, then I know there's a minus sign. Then you'll get your maximum elastic moment. But instead of y, you're going to have to go all the way to the top or bottom and divide by I, which we know is 1.066 10 to the minus 7 meters to the fourth. And I know what C is. We've talked about C. It's just the maximum distance to the top or the bottom. In this case, they're the same. So that would be 0.02. And this we know for A36 steel, it's 250 megapascals. So we'll put that in right here. 250 megapascals. Now we're going to solve for what they call the maximum elastic moment. Get your calculators. Find it for me, please. I got 0. I must have pushed the wrong button. We'll try again. Hey, I got an answer. Did you get the maximum elastic moment is 1332.5 Newton meters? And I'll wait till I hear. I need somebody to say, uh-huh.
I got that number, but I thought it would have been negative.
That's what I'm getting.
Who said that they thought it would be negative? Who said that?
Eric, because in the
Hey,
equation,
Eric, this, wait a minute. No, that's positive. Just a minute, Eric. I'll figure this out. When you solve that, you get a negative. You are right. Now, how do I explain that?
I mean, it makes sense that it would be
Here we
positive.
go. Eric, here we go. That's negative. Because we're coming up here at the top. And remember, the top is compression, right, Eric?
Oh, yeah. Okay, that makes sense. Thank you.
And that you are so very welcome. We have just figured out the maximum elastic moment. Of course, it's the same down here at the bottom. Well, no, that moment is there at the centroid. Okay, well, if that made sense, now what we're going to do is we're going to figure out the fully plastic moment. I hate to erase all that because there's some of you still catching up. There's a little room over here. Now the next thing I'm going to talk about is what they call the fully plastic moment. Things are going good, Susanna. Look, I got all their names over here on the right.
Oh, perfect.
See there?
Yes, yeah, perfect.
Now I pushed unmute all so that anybody can talk to me if they want to. That's fine. And I'm just going ahead with this boring lecture, boring them out of the board. Now the fully plastic moment, they have a symbol for it. It goes like this. See, the maximum elastic moment has this symbol, M with a little y. Do not confuse that subscript with this y here. That y there is the distance from the centroid. This y here is just a subscript, kind of like this p here is just a subscript that denotes the fully plastic moment. Okay, well, I hate to erase all that wonderful stuff, but we got to do the fully plastic moment now. Why don't I make a little table over here? The maximum elastic moment we decided was 1332.5. Okay, so we're going to do the fully plastic moment now. Now you remember when when we had the maximum elastic moment, you had normal stresses like this, and now you got normal stresses, but they're equal to the yield strength stress. They're equal to the 250 megapascal. And the distribution goes kind of like I had before when you have the maximum, what do they call the maximum elastic moment? But see, we're going to do the fully plastic moment. And what happens there is you're going to have fully plastic compression on the whole top half of this thing. And you're going to have fully plastic tension on the whole bottom half of the thing like that. And because it's gone fully, the whole thing is plastic, which would mean the beam will collapse. See, the maximum elastic moment is sort of a danger thing. It's kind of like, hey, don't be getting too much more, don't be making the moment too much more bigger or you're going to be in trouble. Well, when you get to the fully plastic moment, you are in trouble because the whole beam collapses. And we're going to figure out what that collapse, what that moment is. Well, see, this has got a average force. And we can figure out what this force is. That force is equal to your stress times the area. Now the area is 0.02 times 0.02 because the base is 0.02 and the height here is 0.02. And so that force is equal to, well, I don't know. What's 250 megapascals times 0.02 squared? Did you get 100 kilonewtons? Oh, wait.
Yes.
Yeah, good going. Now this is going to have a total force, but it'll be tension, see? It'll be a tension force, and it will equal the same. You got the same numbers. You'll have 100 kilonewtons going this way. Now, when you have two forces that are equal and opposite, they have a special name for that. Two forces that are equal and opposite. I know you've learned this, but you might have forgotten. They call it a nobody's going to say anything. It's called a couple. I know you've heard of couples. Well, we have a couple here. We have a force going that way and an equal force going that way, equal and opposite. And the distance between them, I think, is 0.02. And so the value of this couple is 100 kilonewtons times 0.02 meters. I could almost do that in my head, but it's dangerous. So let me do it on my calculator. Do you get 2,000 Newton meters? We have just figured out the fully plastic moment. If you reach 2,000 Newton meters, your beam collapses if it's A36 steel. I'll give you a moment to digest that, and then I'll show you something else here. Are there any comments or questions so far? I'm waiting. I'm waiting. I unmuted everybody.
They may have themselves muted.
Yeah, they've got themselves muted.
So they need to respond in chat that they understand.
Should I go to chat? I clicked on chat.
So they could type in that yes, understand.
We're in chat, whatever that means. And I've got a lot of wonderful students here. I see Brandon there, and Allison, Cameron, Brian, and a bunch of others. See,
My mic off because my dogs are going after the my neighbor's lawnmower.
oh, okay, that's fine. Thank you.
Yeah, I understand.
Yay, we got somebody that understands. Good going. Was that Kristen again?
No, it's Kylie.
Hey, Kylie, that's the first time I've heard from you. Welcome to our wonderful lecture online here. And my daughters tell me that this lecture will be recorded on some kind of a YouTube channel.
Yeah, it's recording, and we just need to make sure to save it, and then we'll upload it to YouTube.
We're going to save it. We'll upload it to YouTube.
Right.
And somehow we'll tell them how to get on it if they wanted to.
We have the link that.
We have the link.
Is either already in Blackboard or we're going to put it in Blackboard.
We're going to put it in Blackboard. We're going to put the link in Blackboard. You'll see it. You could see, you can watch it over and over.
If you're having trouble sleeping.
Exactly. If they have insomnia, you could just put it on over and over. All right.
Will
now,
the lecture from Tuesday be on there on the YouTube?
I think it is.
The morning one.
Yeah.
Yes. I think the only one missing is yesterday afternoon.
Yeah, I think somehow I fouled up and I didn't put yesterday afternoon physics class on there. But I think all the others are going to be on there. Okay, now let me tell you where we're at right now. If I can find my eraser here. Okay. All right, I need some room here, see. I wish I was in my classroom and I could have the whole dang blackboard to write on and have fun with. But we're going to do the best we know how. And you guys have been very wonderful and patient with me. Now, this has got a name. It's called the maximum. It's a maximum elastic moment, isn't it? And this has a name, and it's called the fully. It's the fully plastic moment. That's what it is. But see, there's one in between. There's a moment in between called the elastic plastic moment. It's part elastic and part plastic. And there's an equation for it. Let's see if I can find it here. Just let me shop around a minute here. It'll be in the section on non-elastic is what they call plastic. Okay, no, inelastic. They call it inelastic. And here's the equation for elastic plastic torque. Now be warned, this only works for rectangles. It's different for some other kind of I-beam or circular beam or reinforced steel, whatever. But for a rectangular beam, it goes like this. It's kind of a complicated formula, but you guys are a really sharp bunch, and I bet we'll be okay with this. Now, they derived this on page 345 in our book, and I would love to derive it with you, but we only have a limited amount of time. Gosh, it's almost 10:30 already. But let me show you an example. Now, we started off with a moment that was, I think, 1,000 Newton meters. And if you're taking diligent notes, like I know you are, we got the stress on that, and it wasn't 250. I forget what it was. Does anybody remember what the stress was when we had 1,000 Newton meter moment?
I think it was the 187.5 megapascal.
Let me see if that's right. I wanted the stress at 1,000. I bet you're right. Oh, gee. I don't remember, but it was less than 250, that's for sure. And my excellent student says it was the stress was 185. Okay. Let's do one here that's in between. Now, 1,500 would be in between, wouldn't it? So far, we've done 1,000 Newton meters, 1332.5 Newton meters, and 2,000 Newton meters bending moment. Let's do 1,500. 1,500 is in between 1332 and 2,000, isn't it? So we're going to put that right here. 1,500 Newton meters. The base is 0.02, the height is 0.04. The yield strength, normal stress is 250 megapascal. 1 minus 4/3. Now what this y sub y is, it's the distance to the end of the elastic region. So you've got an elastic region. Here, I'll draw it for you. what you've got here is it's partially elastic and doing it wrong. You have tension here, and you've gone plastic here, and you have compression here, and you've gone plastic, but you're not totally plastic. You still have an elastic part in the middle. When we were doing the torsion, formula, remember there was an elastic core. Remember that elastic core and the plastic annulus? Well, this is like that. And what this y sub y is, it's the distance from the center to where it goes fully plastic. That y sub y is the, it gives you the size of the elastic region. See, the outside goes plastic, the top and bottom goes plastic, but in the middle, you still have an elastic region. Well, we're going to have to solve for it. H is 0.04, and you have to square it according to this equation. Okay, now we're all going to plug in this equation, and we're going to find out the size of our elastic region there in the middle. I'm going to do it. I want you to do it. Here goes. I'm plugging all this in now. Well, I got an answer of 0.01732 meters. See, from here to here is 0.02 meters. And from here to where it starts to go plastic is 0.01732 meters. So what's that, 20 centimeters? No, that's 20 millimeters. And this is 17 millimeters. So 17 millimeters of this is still elastic. But after that, it's plastic. Now I need somebody to verify that.
That's what I got.
Yay, there's two of us. Yay, there's three of us. So good. We have just taught you about the elastic, the maximum elastic moment, the fully plastic moment, and the elastic plastic moment. Now I've got another 25 minutes, and I want to tell you about some other aspects of this flexure formula. But I'll wait a tiny minute. There's still people probably trying to get that. Now on homework, I need to put this on announcements on Blackboard, don't I? All right.
Now, should that number be negative?
Oh, good question. I didn't get a negative. When I plugged in these numbers, I didn't get a negative.
Well, wouldn't 1 minus 4/3 be a negative?
Well,
Only if y squared over h squared doesn't Only if that's smaller than 3/4.
Yeah, you see, if there's a 1 in there, then the answer to my student is, of course, 1 minus 4/3 is negative. But hey, that's not 1 minus 4/3. It's 1 minus 4/3 times this. Comes out positive, doesn't it? Try it. Plug in that value there, square it, and do that, and you'll get a positive number. It's not negative. But thank you for participating. Well, I need to go on unless there's another comment or question there. All right, well, I guess we're going to go on. I need this room, though. We're going to have to sacrifice some stuff. Say goodbye to all this stuff here. We're going to say goodbye. Last call going.
What page does this all cover? It's 293 to what?
This is on page 345. That formula right there is on page 345. But thank you for asking. Okay, I need the room. We're going to erase this. Are you ready? 5, 4, 3, 2, 1. Blast off. Now, the homework, I need to write that down and put it on your Blackboard. Again, do not turn this in, even though I'm catching up. I think I got all the grades recorded now. But my daughter still hasn't taught me how to grade your stuff efficiently, because those emails was giving me an ulcer. That's going to be your homework. Let me write that down. Here we go. Okay, now here's the last few important topics for today. And that is they have something called a shape factor. And they use a symbol K. I don't know why, but that's their business, I guess. And what it is, it's the ratio of the fully plastic moment to the maximum elastic moment. Now let's put those in and see what we get. The fully plastic moment was 2,000 Newton meters, and the maximum elastic moment was 133 blah 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 Newton meters. So divide those and we'll get the shape factor. Here goes. Did you get 1.5? There's no units because it's just a ratio. That's called the shape factor. Now you'll discover if you have a rectangle, the shape factor is always 1.5. We had a rectangle, and it's the shape factor is 1.5. but you'll discover the shape factor for different shapes. See, there's other shapes. I think this problem here, for instance, if I remember right, is a circle. Well, that's different than a rectangle. And the shape factor will be different. Now, I haven't made my living by designing buildings, but the people that do know about the shape factor of these various beams that they're going to use to hold up the ceilings. Different beams have different shape factors. But now you know what it is. It's just the ratio of the maximum plastic moment, to the fully plastic moment to the maximum elastic moment. Okay. Now there's one more thing here I wanted to show you, and that's called the elastic section modulus. This is in your book someplace, but I don't remember what page. This is a pretty cool thing. There are two formulas for it. The symbol they use is S, and one formula is I over C. Now we know what I is. Uh-oh. Oh no. I think I lost it. Here it is. It's 1.0, a bunch of sixes, 10 to the minus 7 meters to the fourth. Hope you can read my writing. And C on that particular beam was 0.02 meters. So we're going to get the elastic section modulus, and I'll show you what good it is here in just a minute. Did you get 5.33 times 10 to the minus 6 meters cubed? That's what I got. And I'll wait a tiny minute, and I'm hoping that one of you guys will pipe
Yes,
up. Yay, we got somebody. Now there's two formulas for elastic section modulus. The other one goes like this. It goes like this. Oh, I know what that sound is. I need to, guys, I need to plug in this battery on my computer. Just a minute. Just one tiny minute. My battery is getting low. Oh, come on now. I need to plug in my battery. Okay. And no, that's the stinking cell phone. I need this one here. Yeah. Okay. Yay, we got the battery charging now. Oops. No, that's pretty good. Okay, now the other formula goes like this. And let's plug that in and see if you get the same answer. Now, this thing here's got a name. It's called the maximum. It's the maximum elastic moment. And we know what it is. We figured it out. See, I wrote it down over here. And then this here, well, if it's 836 steel, that's 250 megapascals. Now, I want you to divide those and tell me what you get. I'm going to do it. Here goes. Now, this is a screw up here. No, it's not. No, that's correct. I forgot that M is a mega. Let me try this again. Boy, Jove. Here's what I'm getting. I'm getting 5.33 times 10 to the minus 6. Hey, got the same answer. Both of those equations are good. And now let me show you what good it is to have that. But I'll wait a tiny minute because I need feedback. How you guys doing getting that elastic section modulus?
I got both of those answers.
Yay! Let me show you what good it is. And then it's sad, but we're going to have to adjourn. But the good news is you got this homework, but don't turn it in. I'm not ready to take your homework, but I will post the answers. Is that fair enough? You do it, don't peek. And then you look at your answers. I just want you to learn this stuff. Now, listen to me. In the very back of the book, they have elastic section moduli back here someplace. Aha, I found it. There's page after page after page. Here, I'll hold up my book. And there you go. Yeah, can you guys see that? In the back of your book is page after page after page. And there's a little column here that says S. There's a capital S, there's a capital S over here. You turn the pages, there's more of these back here. In the back of your book, look, there's a capital S, there's a capital S. Page after page of elastic section moduli. Now let me show you what it's good for. And there's a little room right here. I'll sacrifice this. Now, you see this bottom equation? You can rewrite that bottom equation like this. Can you guys, algebra students, can you get from here up to that equation? Can you make it? That's a nice little equation, especially if you can look this up. There's tables of this stuff, like for instance, 836, I think it's in the back flap of your book. Yeah, there it is. In the back flap of your book, A36 steel has got a yield strength of 250 megapascals. You can look it up. Or if it's something else, aluminum or stainless or whatever, you can look. And hey, if there's a table of these things, and there is page after page after page of elastic modulus, what's the name of it? Elastic section moduli. Well, you don't have to do any fancy multiplication. All you got to do is just multiply those two and you can get this thing. Remember, this is sort of a warning bending moment. If the bending moment exceeds that, you start going a little bit plastic, because you'll go from elastic to elastic plastic. And if you keep increasing the bending moment, you'll go fully plastic, and then the beam collapses and people could die. People could die. So that's a pretty nifty thing, that elastic section moduli. Well, we've had a wonderful time. I'm so glad we had this time together. And to summarize, we have studied the flexure formula. We have studied the maximum elastic moment. We have studied the fully plastic moment. We've even studied the elastic plastic moment. We have studied the shape factor. The shape factor, it's the ratio of these two moments. And we have studied the elastic section modulus. Do I have, and I gave you some homework, but don't turn it in. I'll put the keys on Blackboard for you when I get around to it. Now, did anybody have any last comments or questions before I figure out how to get off of here?
Since you kind of jumped around so much in chapter 6,
Yes.
Can you upload to Blackboard what was fully covered? Why just type it out? Because you since you explained it, can you type it out in Blackboard?
Thank you so much. I think that's Heath's voice. Is that Heath?
Yes.
Heath, there's some stuff in chapter 6 that's important that I've tried to cover, and there's stuff that we omitted.
So do you recommend we just study chapter 6 on our own?
No,
I'm
going to tell you the stuff that you can omit right now. Thank you for asking. Chapter 6, omit page 310 to, let me flip through here. You can't do everything, especially when we're learning new tricks here. I hate it that we have to skip reinforced concrete, but I can't do everything. And we're going to go to page 343. So Heath, omit those pages in chapter 6. And we will get back to chapter 7 as soon as we can. I don't know how I managed to skip all this fascinating stuff in chapter 6. Now, is there anyone else, any comments or questions?
Professor,
Yes,
will we be moving on to chapter 7 on Tuesday?
I think so, yes.
Okay.
That's my goal.
Okay, so this is all we need to talk about for chapter 6. This concludes chapter 6.
This concludes chapter 6. Very good. Very
Okay.
good. Anybody else? Last call for a comment or question. Well, okay. Adios, muchachos. I'm going to try to bail out of here now if I can. Yeah, here we go. End meeting. Hey, I'm getting the hang of this. End meeting. There it goes. End meeting.